Now that we have the divergence theorem in hand, let's work out an example using the divergence theorem. So let's calculate the integral, the surface integral of this vector field over the boundary of the volume enclosed by all of these things. So, you know, since we just figured out the divergence theorem, clearly we should use the divergence theorem to turn this into a volume integral. But even if we hadn't just figured out the divergence theorem, it should still come to mind that switching this to a volume integral would be a good idea, because if we were going to do this surface integral as it stands, we would need to parameterize all of the boundary surfaces. And as we'll see in a second when we figure out what all of these shapes give us, there are several boundary surfaces, and we'd have to parameterize them each separately. And also, the vector field is very messy, right? There's a lot of stuff going on in this vector field. And so the idea of parameterizing this surface integral is a bit unpleasant. So that should give us an idea, or that should give us the idea to write this surface integral as some other kind of integral. And we have two options available. We can either take a step forward or a step up in dimension using the divergence theorem, or maybe we can take a step backwards in dimension and use Stokes' theorem to write this as a line integral. Well, if we're thinking about using Stokes, so let's call this vector field F. If we're thinking about using Stokes, right, the surface integral that shows up in Stokes' theorem is the surface integral of a curl. So we have to ask ourselves, well, our vector field, is it the curl of some other vector field? Right? And there's a nice way to tell if it is. Remember, if it were the curl of something, then its divergence would be 0, because divergence of curl of something is always 0. So we could just calculate the divergence of this vector field and see if we get 0. So partial m partial x, that's y, plus partial n partial y, which is going to be 2y. This exponential part drops out because it doesn't have any y's in it, plus partial p partial z, but that's 0. So the divergence of this is 3y. So, well, this is not 0. And so, since the divergence of this vector field isn't 0, it can't be the curl of something. So, we can't use Stokes' theorem, right? We might have hoped we could to write this as a line integral, but this isn't the curl of something, so we can't use Stokes' theorem. All right, well, the other option is to use the divergence theorem, but remember, you can only use the divergence theorem if the surface is the boundary of a volume. But look, it explicitly is, right? S is the boundary of the volume enclosed by these surfaces. So our surface is the boundary of a volume, so we can use the divergence theorem. And we've actually already calculated the divergence, so we're partway there already. So the next thing to do to use the divergence theorem is to figure out what is the volume that we need to be integrating over. In other words, we need to see what do these surfaces all enclose. So z equals 0, that's just the xy plane. Y equals 0, that's just the xz plane. So let's look at these other two. Z equals 1 minus x squared. Y doesn't show up in this equation, so if we look just in the xz plane, this is a parabola that opens down like this, right? This top vertex is at height 1. Okay, so that means that if we go now to 3 space, like this, right, in the xz plane we got this parabola like this. In the y direction, this parabola just gets swept in the y direction and we get a parabolic cylinder like this, right? The cylinder that sits on this parabola. Okay, so z equals 0, that's the xy plane, so we just need everything above the xy plane. Y equals 0, the xz plane, so we need everything to the right of the xz plane. And then this thing here, this is a plane, but right, to sort of picture what's going on, we need to have some idea of what this plane looks like. Because x doesn't show up in this equation, we can think of this as living, at first anyway, think of this just as living in the xz plane, or I'm sorry, the yz plane. If we rearrange this, we get z equals 2 minus y. So this, in the yz plane, this looks like this line where these intercepts are 2. So back in the 3D picture, right, we have this plane slicing downwards in this direction. So right, this plane is going to intersect this parabola, looks like this, right? There's this sort of slanted cut coming down this way, right, this direction. Because this intercept is at 2, but this parabola, the highest it gets is 1, the top of the cut is to the right, or to the positive y direction of the z-axis, right? So this cut doesn't pass through the z-axis. Okay, so the volume that we get looks like a parabola, or a parabolic cylinder, but with this sort of diagonal cut out of the side, like this. Okay. So now let's describe this using bounds of integration. Right, the integrand is the divergence of our vector field, which is just 3y. So now we have to decide, how do we want to cut this thing up? If we cut this up so if we put the y integral on the outside, so we're slicing this with planes going this way, and sometimes the top of this cross-section is going to be on the parabola, or the parabolic cylinder, and sometimes it's going to be on the plane that's on the end of this thing. So that's not so nice when it switches from one surface to the other. So let's not do that. Let's not put y on the outside of our integral. How about putting x on the outside of our integral? If we're at a particular x value, the cross-section we get looks like this. And that seems pretty nice, right? That's just a trapezoid. So putting x on the outside seems viable. So what x coordinates will we need? Well, the x coordinates go from -1 here to +1 there. So we need to go from -1 to 1. Okay, next, let's see. Right, we have to decide, do we want to integrate across y, or do we want to integrate across z? Y and z are linked by this linear equation, and I think this is going to work either way, so I don't think it really matters which one we do first. But let's do z first, just because, I don't know, that's how I feel today. So the z coordinates on this cross-section are going to start at 0 and go up to, well, wherever the parabola is for that particular x value. And the parabola is 1 minus x squared. So that's our top z value. And then for our y coordinates, right now we've chosen a particular z value, and we're integrating across this sliver. So the smallest y value across that sliver is 0, and the largest is wherever the plane is. And the plane is, right, it's this plane. So this is y equals 2 minus z. So our top y bound is 2 minus z. Okay, so this is the triple integral that we would need to calculate. You can see that this particular triple integral is totally routine. There's nothing special about this triple integral. And so I think I'll leave evaluating this as an exercise.